On the 3rd of June 2026, at the Beauty Physics Conference in Maastricht, a collaboration of over 1,000 scientists announced that they had found a particle that had been missing for more than half a century. It is called the Omega CC+, the third and final member of a family of baryons that physicists first predicted in the years after the quark model was born. Two of its siblings had already been found, one in 2017 and another just 3 months earlier, and now, with the last one in hand, the ground-state doubly charmed baryon family is complete. That prediction was made over 50 years ago, and the technology needed to prove it right did not exist then. So how did physicists go from sketching a family of particles on paper to actually holding all three in their data? Everything around you, the air you are breathing, the screen you are looking at, the bones in your hands, is built from baryons. A baryon is a particle made of 3 smaller building blocks called quarks, bound together by gluons through the strong interaction. And the most familiar baryons are the proton and the neutron, the 2 particles that sit inside every atomic nucleus in the universe. A proton is built from 2 up quarks and 1 down quark, and a neutron swaps one of those up quarks for a second down quark, and that tiny difference is enough to give them completely different electrical charges and completely different roles in chemistry. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom, arranged in 3 generations of increasing mass. And in principle, you can combine any 3 of them into a baryon. The question that consumed particle physicists in the middle of the 20th century was whether nature actually uses all of those combinations, or only some of them. By the late 1950s, experiments were turning up new particles so fast that nobody had a clean way to organize them. The bubble chambers and cosmic ray plates of the era were spitting out hadrons faster than theorists could name them, and Enrico Fermi reportedly grumbled that if he'd wanted to memorize this many particles, he would have become a botanist. It was a bit like discovering dozens of chemical elements without having a periodic table to sort them into. Then, in 1961, 2 theorists working independently came up with an answer. Murray Gell-Mann at Caltech and Yuval Ne'eman in London both proposed a classification scheme that Gell-Mann christened the Eightfold Way, after the Buddhist path to enlightenment. At the 1962 CERN conference, the 2 of them used it to make a concrete prediction. It did, for subatomic particles, what Mendeleev's table had done for elements a century earlier. It sorted the known baryons and mesons into neat geometric families based on an underlying symmetry. And the patterns were so clean, so symmetric, that empty slots in the diagram stood out immediately. If the scheme was right, those empty slots told you exactly which particles you should be looking for. Particles with specific masses and specific properties had to exist to fill them. The most striking empty slot sat at the bottom of a triangular arrangement called the baryon decuplet, and Gell-Mann announced that a particle containing 3 strange quarks, which he named the Omega-, had to be sitting there. He predicted its mass, its charge, and even how it would decay. 2 years later, in 1964, a team at Brookhaven National Laboratory in New York found it in a single bubble chamber photograph, one image capturing the tracks of a particle that had been conjured into existence by a high-energy collision and then decayed in exactly the way the theory said it would. That single photograph did something enormous for physics. It proved that the quark model was not just a filing system for particles that had already been found. It was a prediction engine, capable of telling you what exists before anyone has ever seen it. And once physicists trusted that engine, they started asking a much bigger question. What else is the model predicting that we have not found yet? One of the things I find fascinating about science is that every so often, someone figures out a better way to organize knowledge. And once that happens, patterns start appearing that nobody noticed before. The periodic table did it for chemistry. The quark model did it for particle physics. Suddenly, scientists weren't just explaining what they had already found. They could predict what was still missing. That idea of collecting human knowledge into one place reminded me of something I've genuinely enjoyed looking through recently. It's called The Book, The Ultimate Guide to Rebuilding a Civilization by Hungry Minds. What I like about it is that it isn't trying to be another science textbook. It's more like a visual collection of humanity's biggest discoveries and inventions, all brought together in one beautifully designed book. You can open it almost anywhere and end up learning something interesting, whether it's engineering, astronomy, architecture, mathematics, or the history behind technologies we use every day. The artwork is probably my favorite part. Every page mixes detailed engineering drawings with artwork inspired by medieval manuscripts, so it feels like you're reading something that's both modern and ancient at the same time. It's honestly one of those books you'll leave on your desk because people immediately want to pick it up and start flipping through it. It has more than 400 pages covering over 180 topics, and there's even a hidden quest built into the book that readers can discover as they explore it. I won't spoil it, but it's a nice little surprise. After seeing the quality of it, it's not hard to understand why it raised over $2.3 million on Kickstarter and Indiegogo and went on to become a bestseller. So if you're the kind of person who enjoys the topics we talk about on this channel, or you're looking for a genuinely unique gift for someone who's endlessly curious, I think you'll appreciate this one. You can check it out using the link in the description, and if you use my code FEXEL, you'll get 10% off. In November 1974, two laboratories on opposite sides of the United States found the same particle at almost the same time. A team at Brookhaven, led by Samuel Ting, and a team at SLAC, led by Burton Richter, both detected a new meson that was far heavier than anything the existing three-quark flavors could explain, and its discovery was so sudden and so disruptive that physicists started calling that period the November Revolution. The particle was the J Persei, and what it revealed was that a fourth flavor of quark existed, one that theorists had already been speculating about for years. They called it charm. The moment charm was confirmed, the quark model's prediction engine kicked into a much higher gear. If you now had 4 flavors of quark to work with instead of 3, the number of possible baryon combinations expanded dramatically, and theorists began filling in the new slots on the chart. Among the most interesting predictions were a set of baryons that contained not just one charm quark, which would be unusual enough, but 2 of them sitting together inside the same particle. These doubly charmed baryons would be something genuinely new, because the 2 heavy charm quarks would behave very differently from the lighter quarks that made up all the baryons physicists had studied so far. The prediction was specific. There should be exactly 3 of them, forming what physicists call an SU3 triplet. The first would contain 2 charm quarks and 1 up quark, giving it a double positive charge, and it was named the Xi-CC++. The second would swap that up quark for a down quark, bringing the charge down by 1, and it was named the Xi-CC+. The third would swap in a strange quark instead, and it was named the Omega-CC+. Theorists calculated that all 3 should have masses somewhere in the range of 3,450 to 3,750 mega-electron volts per c squared, roughly 4 times heavier than a proton, with most quark model calculations clustering around 3,600 mega-electron volts per c squared. What made these particles especially exciting for physicists was not just their novelty, it was what their internal structure could teach us about the strong force. In an ordinary baryon like a proton, all 3 quarks are relatively light, and they move around each other in a complicated, tangled dance that is extremely difficult to calculate from first principles. In a doubly charmed baryon, the picture changes completely. The 2 charm quarks are so much heavier than the third quark that they sit almost motionless at the center of the particle, and the lighter quark orbits around them at a much greater speed. The whole arrangement starts to resemble a tiny atom, with the charm-charm pair playing the role of the nucleus and the light quark playing the role of the electron. That resemblance is not just a poetic comparison. It means that certain calculations in quantum chromodynamics, the notoriously difficult theory of the strong force, become much more manageable, because you can separate the slow, heavy physics at the center from the fast, light physics at the edges. Finding these particles and measuring their masses would give theorists a clean laboratory for testing how quarks are actually bound together, something that ordinary baryons are too messy to reveal on their own. The problem was that no experiment running in the 1970s or 1980s could produce enough energy or collect enough data to have any realistic chance of seeing them. The doubly charmed baryons were sitting there on the chart, three empty slots with predicted masses and predicted properties, and the technology needed to fill those slots simply did not exist yet. For nearly 30 years after the charm quark was confirmed, the doubly charmed baryons remained purely theoretical. Physicists knew what they should look like and roughly how heavy they should be. And every few years, someone would run a new lattice calculation or update a quark model prediction, and the numbers would shift a little, and the particles would continue to not show up in any detector. Then, in 2002, a fixed target experiment at Fermilab called CELEX announced that they had found one. The claim was bold. CELEX reported a signal of about 15.9 events above a background of roughly 6.1, which gave them a statistical significance of 6.3 sigma, well above the threshold that physicists normally require before using the word discovery. The particle they said they had found was the Xct+, the doubly charmed baryon with two charm quarks and one down quark, and they measured its mass at 3,519 megaelectron volts per c squared. They even confirmed the signal in a second, independent decay mode with a significance of 4.8 sigma, which in most circumstances would have been enough to put the matter to rest. It did not put the matter to rest. Almost immediately, theorists started raising concerns. The lifetime that CELEX measured was less than 33 femtoseconds, which was significantly shorter than what any theoretical model predicted for this particle. And the production rate was strange, somewhere between 10 and 100 times higher than what physicists expected from the collision energies CELEX was working with. A particle being produced that abundantly at those energies would have implied a production mechanism that nobody had accounted for, and while that was not impossible, it was difficult to reconcile with everything else that was known about charm quark physics. What made things worse was what happened next, or rather, what did not happen next. Over the following years, several independent experiments went looking for the same signal. Focus, another fixed target experiment at Fermilab, searched for it and found nothing. The Babar experiment at SLAC searched for it and found nothing. The Bell experiment in Japan searched for it and found nothing. Each of these experiments had large charm baryon samples and the sensitivity to see a signal at the mass and production rate that CELEX had reported, and none of them could reproduce the result. The CELEX claim was never formally retracted, and the collaboration kept standing behind their data. What happened instead was something more awkward and more common in experimental physics than most people outside the field realize. It's the particle physics version of the replication crisis that's shaken psychology and biomedicine over the last decade. A single positive result, taken on its own, is a much weaker piece of evidence than the same result reproduced across independent experiments, and statistical significance alone can't rescue a measurement that nobody else can see. The result entered a kind of scientific limbo. It sat in the literature with its 6.3 sigma significance and its confirmation in a second decay mode, and at the same time it sat under a growing weight of non-replication, and the community slowly moved on without settling the question one way or the other. For 15 years, the doubly charmed baryons remained in that uncomfortable space, predicted by theory, claimed by one experiment, and unseen by everyone else. Underneath the French-Swiss border, straddling the outskirts of Geneva, the Large Hadron Collider sends protons hurtling around a 27-kilometer ring at velocities that approach the speed of light. When those protons smash into each other, the energy released is enough to conjure particles into existence that would never appear under ordinary conditions. Particles that flash in and out of reality in fractions of a trillionth of a second and leave nothing behind except faint tracks in a detector. One of those detectors is the LHCb, a machine built specifically to study how matter and antimatter behave differently. And in July 2017, it found something that the field had been chasing for decades. The signal contained 313 events, sitting cleanly above the background noise with a statistical significance that exceeded 12 sigma, which is so far beyond the discovery threshold that the probability of it being a random fluctuation is essentially zero. The particle was a baryon containing 2 charm quarks and 1 up quark, and its mass came in at 3,621 megaelectron volts per c squared, almost exactly where the quark model had predicted it would be. It was the Xi-CC++, the first member of the doubly charmed triplet, and it was the first time any experiment had conclusively observed a baryon with 2 heavy quarks inside it. It also quietly closed the book on the CELX question. The mass that CELX had reported 15 years earlier was 3,519 megaelectron volts per c squared, more than 100 MeV below the LHCb measurement, and that gap was far too large for the two results to be describing the same family of particles. Whatever CELX had seen in their data, the doubly charmed baryon that actually existed in nature was sitting at a different mass entirely. Finding one member of the triplet was a landmark, and it confirmed that the quark model's 50-year-old prediction was real. Finding the other two was going to be harder, and the reason came down to lifetimes. The Xi-CC+, the second member of the family, was predicted to live roughly 6 times less long than its sibling, because subtle quantum effects inside the particle cause its decay channels to interfere constructively rather than destructively, which speeds the whole process up. A lifetime that short, somewhere around 45 femtoseconds, means the particle travels a fraction of a millimeter before it falls apart, leaving fewer clean tracks in the detector and making it much more difficult to distinguish from background noise. The LHCb detector, as it existed in 2017, was not sensitive enough to reliably catch something that brief, so the collaboration rebuilt it. During the second long shutdown of the LHC, which ran from 2019 through 2022, the LHCb detector underwent a comprehensive upgrade. The silicon microstrip sensors in the vertex detector were replaced with pixel sensors and brought physically closer to the collision point from 8.4 millimeters down to 5.1 millimeters, which improved the resolution of track measurements by 40%. The entire readout system was overhauled so the detector could operate at 5 times the luminosity of its earlier runs. And by the time commissioning was finished at the end of 2023, the upgraded machine was effectively taking 40 million photographs of particle collisions every second. The upgrade paid off almost immediately. Using collision data collected in 2024, the LHCb team identified the ZCC+ in the decay products of proton-proton collisions. Measuring its mass at 3,619.97 megaelectron volts per c squared, which is almost identical to the Xi-CC++ mass, exactly as isospin symmetry predicts. The significance was 7 sigma, comfortably above the discovery threshold, and the result was announced at the Rencontre de Morion conference on the 17th of March 2026. It was the first new particle found with the upgraded detector, and the 8th hadron discovered at the LHC overall. LHCb spokesperson Vincenzo Vagnoni called it the first of many expected insights from the new machine. 3 months later, at the Beauty 2026 conference in Maastricht, the third and final member arrived. The Omega CC+, containing 2 charm quarks and 1 strange quark, appeared as a clear peak in the data observed through its decay into an Omega C baryon and a pion. The particle that Gell-Mann's extended quark model had predicted over 50 years earlier, the one that sits in the same logical position as the Omega- that confirmed the eightfold wave back in 1964, had finally been seen. In 1964, it took 1 bubble chamber photograph at Brookhaven to complete the baryon decuplet. In 2026, it took a detector capturing 40 million images every second at CERN to complete the doubly charmed triplet. The scale of the technology changed beyond recognition, but the underlying logic was identical. A theory predicted that a family of particles had to exist. Experiments went hunting, and the last member was the one that proved the prediction was right all along. So what can physicists actually do now that they have all 3 members of the family sitting in their data? The short answer is that they can start comparing them against each other. And those comparisons are where the real physics lives. Each of the three doubly charmed baryons has the same pair of heavy charm quarks at its center, and the only thing that changes from one to the next is the identity of the lighter quark orbiting around them. In the GCC++, it is an up quark, in the GCC+, it is a down quark, and in the Omega CC+, it is a strange quark. Because the strong force is supposed to treat all quark flavors the same way at short distances, a property called flavor independence, the differences in mass and lifetime between these three particles are driven almost entirely by the differences between the lighter quarks themselves. That means physicists can measure those differences and use them to test whether QCD's predictions about flavor independence actually hold up when you put real numbers into the equations. The first two members already showed a mass splitting that is consistent with isospin symmetry, confirming excellent alignment with theoretical expectations for swapping a down quark for an up quark. Adding the strange quark measurement from the Omega CC+ now gives theorists a third data point. And because the strange quark is significantly heavier than either up or down, the mass shift should be much larger and much more revealing about how the strong force responds to quark mass. None of this work is finished. The measurements announced so far are based on data collected during 2024, and the LHC is still running and still collecting collisions. Tim Gershon, the University of Warwick physicist, who takes over as LHCb lead in July 2026, has said that the March discovery was just the first of many expected insights from the upgraded detector. The machine is scheduled to go into its third long shutdown between 2026 and 2028, and a second major upgrade is planned for implementation during long shutdown 4, which runs from 2033 to 2035. That upgrade will replace another generation of detector components and data acquisition systems, pushing the experiment's sensitivity even further. Beyond that, the high luminosity LHC program is expected to deliver datasets roughly 15 times larger than what the current run has produced, which will open the door to precision measurements that are simply not possible with the statistics available today. And there are still empty slots on the chart. The quark model predicts equivalent families of baryons built with 2 bottom quarks instead of 2 charm quarks, and mixed families containing 1 charm and 1 bottom quark together. Bottom quarks are roughly 3 times heavier than charm quarks, which means the particles they form are even more massive, even shorter lived, and even harder to produce in sufficient numbers. No doubly bottom baryon has ever been observed, and finding them will require the kind of luminosity and detector precision that only the next generation of upgrades can deliver. The doubly charmed triplet took 50 years to complete. The doubly bottom family is likely to be a longer wait, but the prediction is already on the chart, and if the history of this field teaches anything, it is that the predictions tend to be right. What makes the doubly charmed story worth telling is not just that the prediction turned out to be correct, because by now, most physicists expected that it would be. What makes it worth telling is how long the gap was between knowing something should exist and actually being able to see it, and how that gap was filled not by a single dramatic moment, but by decades of incremental progress in detector technology, data collection, and computational power, all converging on a set of particles that live for less time than it takes light to cross the width of a human hair. The quark model said they were there. The machines finally caught up, and the chart still has empty slots. Families of particles built from bottom quarks, combinations of charm and bottom together. Configurations that the model insists are real and that no detector has ever registered. Every time one of those slots gets filled, the pattern becomes a little more complete, and the edges of what we do not yet understand become a little more visible. The doubly charmed baryons are not the end of the story. They are the part of the story where the prediction engine proved, once again, that it knows something about the universe that we are still catching up to.